This is another paper from 1916 where Einstein shows how to derive the general equations of relativity from a variational principle. Let the gravitational field be described as usual by the metric tensor g mu nu with lower indices, or also its inverse g mu nu with upper indices. And let matter, including the electromagnetic field, be described by any number of space-time functions that I will call q rho, like this, where rho is an index that can take the values 1, 2, 3, 4, and so on and so forth. This index here, q rho. So let me try to draw it more clearly. Rho, like this. Now let L be a function of the g mu nu and also derivatives of the g mu nu, so g mu nu sigma. And let me remind this notation. G mu nu sigma is defined as the derivative of g mu nu with respect to x sigma, and also g mu nu sigma tau, which are the second derivatives. So second derivative of g mu nu with respect to x sigma with respect to x tau, like this. And it also depends on q rho and also on the derivatives of q rho, so q rho alpha, and this is by definition derivative of q rho with respect to x alpha, like this. Now the variational principle in this case can be written in this fashion, so variation of integral L d tau equal to 0. This gives us many differential equations as there are functions g mu nu and q rho to be defined. If the g mu nu and q rho are varied independently of one another, and in such a way that at the boundary of integration we have delta q rho equal to 0, and also the variation of g mu nu is equal to 0, and derivative with respect to x sigma variation of g mu nu is 0, then we know that the boundary terms vanish, and we now assume that L, this function here, is linear in the g mu nu, and that the coefficients of the second derivatives depend solely on the g mu nu. And why is this assumption true? Well, it is true because we know the form that the equation should have. The relativistic equations contain the Ricci tensor, and in particular a contraction of the Ricci tensor, which is the Ricci scalar. So we must have that in mind. In this case, which is the case of interest for general relativity, the variational principle can be rewritten after partial integration. So we can integrate by parts, because the integral L d tau will be rewritten like this: integral of L star d tau plus f, where f denotes an integral over the boundary of the domain in question, and L star here depends solely on the metric tensor g mu nu, the derivative of the metric tensor, so g mu nu sigma. It will depend on q rho and on q rho alpha. So as you can see, L star does not depend anymore on the second derivatives of g mu nu. It only depends on the first derivative and on the metric tensor itself, because after partial integration we have removed the dependence upon the second derivatives. So the variational principle can be rewritten in this case like this: variation of L d tau will be equal to the variation of L star d tau, since the variation of f is equal to 0. If we carry out the variation, we get this. So the variation of integral L star d tau can be rewritten as integral d tau of derivative of L star with respect to G mu nu, variation of G mu nu plus derivative of L star with respect to G mu nu alpha, variation of G mu nu alpha plus derivative of L star with respect to Q rho, variation of Q rho plus, and here we have the derivative of L star with respect to Q rho alpha, variation of Q rho alpha. And this is equal to, now we can rewrite this in different terms, integral d tau, derivative of L star with respect to G mu nu minus derivative with respect to X alpha of derivative of L star with respect to G mu nu alpha, variation of G mu nu, and then we have plus integral d tau of dl star dq rho minus derivative with respect to X alpha of dl star with respect to q rho alpha times variation of q rho. And we also have a boundary term like this, integral of derivative with respect to X alpha dl star with respect to G mu nu alpha, variation of G mu nu plus derivative L star with respect to Q rho alpha d tau. And this is a boundary term because we have to integrate this divergence. So when we integrate, we only get the boundary term, and that is 0 because we know that the variations are 0 at the boundary. So from this, we get two equations of this kind. We have derivative with respect to X alpha of derivative of L star with respect to G mu nu alpha minus derivative L star with respect to G mu nu equal to 0. And we also get another equation of this kind, derivative with respect to X alpha, derivative of L star with respect to Q rho alpha minus derivative of L star with respect to Q rho equal to 0. Now we suppose that L can be rewritten like this, as a sum of two different scalars, R and M. So we have R plus M. Or alternatively, we can also rewrite L star as R star plus M star, where the difference between L and L star and R star and M star is just the same. So we define these quantities after partial integration. And M star is actually equal to M because M does not depend on the second derivatives of the metric. So we are going to suppose that R depends on, so let me do it below. R will depend on G mu nu, the derivatives of the G mu nu, so G mu nu sigma, and the second derivatives, G mu nu sigma tau. Whereas R star will only depend on G mu nu sigma, only on these first two terms, because as I said, after a partial integration, we are going to remove the dependence from this term, whereas M or M star, because they are the same, they will depend on the metric tensor G mu nu, Q rho, and Q rho alpha. So this is m, which is a function of these quantities. Therefore, these two equations here, in this case, can be rewritten in this form. We can rewrite them as derivative with respect to x alpha of derivative of r star with respect to g mu nu alpha minus derivative of r star with respect to g mu nu equal to the derivative of m with respect to g mu nu, and then we have derivative with respect to x alpha of derivative of m with respect to q rho alpha minus derivative of m with respect to q rho, and this is equal to 0. Now this second equation here, it could be possibly more general than this if the q rho were not independent, for example, and or the function m depended upon more than just the first derivatives of the q rho. But this is not relevant to us, since we will focus only on this equation here. Now, the variational principle can be written so that the invariants are emphasized, and in particular, if we rewrite the integral L d tau like this, we are going to rewrite it as, since L is equal to R plus M, I'm going to write R, and I'm going to divide it by the square root of minus G, then we have plus M divided by the square root of minus G, and then we multiply by square root of minus G d tau. We know that this volume here is an invariant if we multiply it by the square root of minus G. And therefore, also this one should be an invariant, and this one here should be an invariant. So R divided by the square root of minus G must be equal, apart from some constant factor, to the scalar that's derived from the Riemann's tensor. And as I said, this is related to the Ricci scalar. Now, let's assume that we have a transformation. So we are going to do some steps here. This is what Einstein did in his article. He considered a transformation of this kind. So we are going from the coordinates x nu to the coordinates x prime nu. Let's call it x prime. And in particular, x prime nu is equal to x nu plus a small change that I will call delta x nu. So this delta x nu should be considered as a small change with respect to the coordinates. So we are going to alter the coordinates just by a small quantity. This is just a vector that contains 4 coordinates. Now we also want to find, if we change the coordinates like this, what is the change delta g mu nu? How do we find that? Well, we know that g mu nu is a tensor, and if we want to express g mu nu in the new coordinates x prime, we know that we have a rule. So this is equal to g alpha beta in the old coordinate x, and then we multiply by dx prime mu with respect to x alpha, and then we have the derivative of x prime mu with respect to x beta. Now we can substitute in place of x prime here the transformation, and therefore we can rewrite this as g alpha beta of x, and here we have delta mu alpha from this term. So if we take the derivative of this first part plus derivative of delta x mu with respect to x alpha, and then we also multiply by delta nu beta plus derivative of delta x nu with respect to x beta. Now this is equal to, if we neglect second order quantities, and the second order quantities are given by the multiplication between this term and this term, So if we multiply them together, we get a second order quantity that we can neglect. And here we get equal to g mu nu of x plus g alpha nu of x derivative dx mu with respect to x alpha plus g mu beta of x derivative of delta x nu with respect to x beta. And now we can rewrite this equation like this: g mu nu of x prime minus g mu nu of x, and this is exactly what we call delta g mu nu. It is the change in the tensor g mu nu when we change the coordinates from x to x prime. And this is equal to g alpha nu derivative of dx mu with respect to alpha, to x alpha, plus g mu beta derivative of delta x nu with respect to x beta. Now we want to do something similar also for the derivatives of the metric tensor. And in particular, if we consider g mu nu sigma, we want to find what is the small change in this term. So let's start from derivative of g mu nu with respect to x prime sigma evaluated at x prime. So this will be equal to, first we are going to change this gradient here. The gradient will change like this. We have the chain rule dx gamma with respect to x prime sigma derivative with respect to x gamma of, and here we are going to consider g mu nu x prime as given by the formula that we have found above. So this will be given by g mu nu of x plus the small change in g mu nu of x, like this, right? And also we know that this term can also be rewritten like this, because x gamma is equal to x prime gamma minus delta x gamma, right? So delta x gamma with respect to x prime sigma will be given by delta gamma sigma minus derivative of delta x gamma with respect to x prime sigma. And so if we do this calculation here, we get derivative of g mu nu with respect to x sigma of x plus derivative of delta g mu nu of x with respect to x sigma minus derivative of delta x gamma with respect to x prime sigma times derivative of g mu nu with respect to x gamma of x minus derivative of delta x gamma with respect to x prime sigma times delta g mu nu of x. And now notice that this last term here is a quantity of second order because we have two deltas here. Therefore, this can be neglected. And from here, if we subtract this term from both sides, we get exactly the variation of g mu nu sigma, because also according to our notation, this can also be written as g mu nu sigma, and in this case it will be a function of x, whereas on the left here we have the same quantity g mu nu sigma, and in this case it is a function of x prime. So when we subtract this term here from this term, we get g mu nu sigma of x prime minus g mu nu sigma of x, and that's exactly the change that we have in g mu nu sigma. This will be equal to derivative of g mu nu with respect to x prime sigma of x prime minus derivative of g mu nu with respect to x sigma of x, and this will be equal to the derivative of the change g mu nu, so delta g mu nu with respect to x sigma minus, and here we have derivative of delta x gamma with respect to x prime sigma times derivative of g mu nu with respect to x gamma. But now this term here can also be rewritten using the chain rule. In particular, this is also equal to derivative of x xi with respect to x prime sigma times the derivative of delta x gamma with respect to x xi, and this is equal to delta xi sigma minus derivative of delta x xi with respect to x prime sigma, which multiplies d delta x gamma with respect to x xi. But now you see that if we multiply this term with this term, we will get a second order quantity. So we can neglect that second order quantity, and therefore this is approximately equal to derivative of delta x gamma with respect to x sigma, like this. So we have found that delta g mu nu sigma is equal to derivative of delta g mu nu with respect to x sigma minus derivative of delta x gamma with respect to x sigma multiplied by g mu nu gamma. Now with the expressions for delta g mu nu and delta g mu nu sigma that we have found, we can calculate delta r star also. Or in particular, we are interested in this term that I will show you here, square root of minus g times the small change in the quantity r star over square root of minus g. And we can treat this delta here as a small change, so it behaves very similarly to a derivative. So we can write this as delta r star minus 1 over square root of minus g variation or small change of square root of minus g times r star. This here can be rewritten like this. So this is also equal to the small change in minus g divided by 2 times minus g, which is equal to 1/2 small change in g over g. Now for the properties that we have found in previous videos, this can also be written as minus 1/2 g mu nu times the small change in g mu nu with upper indices here. So this can be rewritten as, let me go below, equal to delta r star plus 1/2 of g mu nu delta g mu nu r star, and we can rewrite delta r star also like this. It's the derivative of r star with respect to g mu nu delta g mu nu plus derivative of r star with respect to g mu nu sigma times delta g mu nu sigma. Therefore, now we can rewrite this term, square root of minus g times small change in r divided by the square root of minus g, like this. It is dr star over dg mu nu times g mu alpha derivative of delta x nu with respect to x alpha. So in here I'm just using the definition for delta g mu nu Actually, it is not really a definition, it is what we have found earlier, plus g nu alpha, derivative of delta x nu with respect to x alpha, plus derivative of r star with respect to g mu nu sigma. And in here we are going to replace, instead of this term here, we are going to put what we have derived earlier. So we have the derivative with respect to x sigma. Here we have a small change in the metric tensor, which can be written as g mu alpha, derivative of delta x nu with respect to x alpha, plus g nu alpha, derivative of delta x mu with respect to x alpha, minus g mu nu alpha, derivative of delta x mu with respect to x sigma. And we also have plus this part here, this part that we have here. So we have 1/2 times g mu nu times the small change in g mu nu, as you see there. And if we replace what we have found, we have g mu alpha, derivative of delta x nu with respect to x alpha, plus g nu alpha, derivative of delta x mu with respect to x alpha times r star. Now, this seems quite complicated, but we have to do some steps, and then we will also use these results. So here we get, if you check, the first term is symmetric, so we get 2 times derivative of r star with respect to g mu alpha, derivative of delta x nu with respect to x alpha, plus derivative of r star with respect to g mu nu sigma times g mu alpha sigma times derivative of delta x nu with respect to x alpha plus g nu alpha sigma times the derivative of delta x mu with respect to x alpha plus, then here we have plus g mu alpha d squared delta x nu dx sigma dx alpha plus g nu alpha d squared delta x mu with respect to x sigma with respect to x alpha minus g mu nu alpha d delta x alpha with respect to x sigma plus derivative of delta x nu with respect to alpha. Let me do it here. With respect to alpha, delta alpha nu r star. Now let's do some more algebra. This is just some algebra. We have 2 d r star with respect to g mu sigma. So I'm also changing the indices. I'm relabeling them, times g mu nu times derivative of delta x sigma with respect to x nu plus 2 dr star with respect to g mu sigma alpha g mu nu alpha, derivative of delta x sigma with respect to x nu plus 2 derivative of r star with respect to g mu sigma alpha times g mu nu times, we also have the second derivative of delta x sigma with respect to, let me do it here, with respect to x alpha and x nu. And then we have plus, let me go below, minus derivative of r star with respect to g mu alpha nu g mu alpha sigma derivative of delta x sigma with respect to x nu plus derivative of delta x sigma with respect to x nu delta nu sigma r star. Now this can be rewritten in this fashion. We have 2 dr star with respect to g mu sigma times g mu nu plus 2 dr star with respect to g mu sigma alpha times g mu nu alpha plus r star delta nu sigma plus, actually minus, dr star with respect to g mu alpha nu times g mu alpha sigma, which multiplies the derivative of delta x sigma with respect to x nu. So I have just simply collected this factor here from a bunch of terms, and then we are left with one more term here, which is twice the derivative of r star with respect to g mu sigma alpha times g mu nu, and this multiplies the second derivative of delta x sigma with respect to x alpha and x nu. Now, Einstein calls this term here simply like this, S nu sigma. Now, we know that r over the square root of minus g is an invariant, and also the integral of r over square root of minus g times the square root of minus g d tau is an invariant. And also pay attention to the fact that here I'm considering r without the star, because remember that the only difference between r and r star is a partial integration, an integration by parts. When we integrate this by parts, in fact, we get r star over square root of minus g times square root of minus g d tau plus some boundary term f. And this boundary term depends on g mu nu and the derivatives of g mu nu, but does not depend on the second derivatives of g mu nu. Now, the first derivatives of g mu nu are proportional to the second derivatives of the coordinates. So, if we choose the coordinates such that they are linear, and also that delta x nu is equal to 0 at the boundary, we know that in this case this will be 0, and therefore we get that this is also an invariant, right? Now remember that we have found this result, square root of minus g times delta of r star over square root of minus g is equal to s nu sigma that we have defined above, derivative of delta x sigma with respect to x nu plus twice derivative of r star with respect to g mu sigma alpha, g mu nu, second derivative of delta x sigma with respect to x alpha, x nu. Now, as I said, if the coordinates are linear, this term here will be 0 because we have the second derivative of delta x sigma. But if the coordinates are linear, of course, that term will be 0. And since these terms here are arbitrary and this quantity on the left is 0 because here we have an invariant and we are considering here the variation of an invariant, the change of an invariant is 0. So this result should be 0, and since, as I said, these are arbitrary, it means that S nu sigma is also 0. Now, if we consider this term again, that we know to be 0, but if we integrate that term like this, dr star with respect to g mu sigma alpha times g mu nu, second derivative of delta x sigma with respect to x alpha, with respect to x nu, d tau, we know that this is 0. But this can be useful because now we can integrate this expression by parts twice. And if we integrate by parts twice, this operator here of the second derivative will move and it will have to differentiate this part here, this term. So, considering that the variation is arbitrary, we get this equation here. Second derivative with respect to x nu and x alpha of dr star dg mu sigma alpha times g mu nu is equal to 0. Now, let's rewrite one of the equations that we derived earlier. In particular, we have already derived this equation here, d over dx alpha, dr star with respect to g mu nu alpha minus dr star dg mu nu equal to dm with respect to g mu nu. This is a field equation that we have found earlier. Now we multiply this equation by g mu sigma, and we also exchange the indices sigma and nu. In this case, if we do that, we can rewrite the equation like this: g mu nu derivative with respect to x alpha, derivative of r star with respect to g mu sigma alpha minus g mu nu dr star with respect to g mu sigma equal to g mu nu derivative of m with respect to g mu sigma. But this can also be written in this fashion: derivative with respect to x alpha of g mu nu times dr star dg mu sigma alpha equal to g mu nu alpha dr star with respect to dg mu sigma alpha plus g mu nu dr star with respect to g mu sigma plus g mu nu dm over dg mu sigma, like this. Now we are going to call these first two terms here like this: minus t nu sigma, lowercase t, whereas this quantity here we'll call minus capital T nu sigma, where lowercase t will indicate the energy components of the gravitational field, whereas capital T will indicate the energy components of matter. So we have found this derivative with respect to x alpha, g mu nu dr star dg mu sigma alpha equal to minus t nu sigma plus t nu sigma, lowercase t and uppercase t. But we know that if we take the derivative with respect to x nu of this term, so if we take partial with respect to x nu and partial with respect to x nu, of course, here as well, we get 0. We know that this is 0. This term here on the left is 0. But why is that? Well, that's quite easy. We have already found that expression here. It's exactly this one, right here. So we have found that this quantity here is 0. But what is that? That just expresses the law of conservation of momentum and energy, which Einstein previously derived in another paper. But now we can also rewrite lowercase t nu sigma in another fashion. So we know that by definition this is minus dr star dg mu sigma alpha times g mu nu alpha plus derivative of r star with respect to g mu sigma times g mu nu, and we know from the expression of s nu sigma, so let me write it here, s nu sigma, we know that s nu sigma is equal to 0 according to the choices that we have made and the expressions of s nu sigma. If we set it equal to 0, we can rewrite these two terms which appear in the expression for s nu sigma in this way. This is equal to 1/2 r star delta nu sigma minus derivative of r star with respect to g mu alpha nu times g mu alpha sigma, like this. Now let's consider the derivative with respect to x nu of uppercase T nu sigma, which from the law of conservation is equal to minus derivative with respect to x nu of lowercase t nu sigma, and from what we have found this is equal to minus 1/2 derivative of r star with respect to x sigma minus derivative with respect to x nu of derivative of r star with respect to g mu alpha nu g mu alpha sigma, and this is equal to, let's do it below, equal to minus 1/2 derivative of r star with respect to x sigma minus derivative with respect to x nu derivative of r star with respect to g mu alpha nu times g mu alpha sigma minus derivative of r star with respect to g mu alpha nu times derivative of g mu alpha sigma with respect to x nu, like this. If you just do the differentiation above, this is what you get. But this derivative here can also be written as derivative of g mu alpha nu with respect to x sigma, because the order of differentiation does not matter. And remember that this expression here can also be written as the derivative of g mu alpha with respect to x nu. So we have a second derivative if you also take into account the derivative with respect to x sigma. So the order of differentiation does not matter. We can exchange the two differentiations. And also remember that from the field equations, this term can be rewritten as derivative of r star with respect to g mu alpha plus derivative of m with respect to g mu alpha. And therefore, this can be rewritten like this. This is equal to minus 1/2 dr star with respect to x sigma minus derivative of r star with respect to g mu alpha, derivative of g mu alpha with respect to x sigma minus derivative of r star with respect to g mu alpha nu times derivative of g mu alpha nu with respect to x sigma minus derivative of m with respect to g mu alpha times g mu alpha sigma. But now these two terms together, if we put them together according to the chain rule, this is equal to minus dr star with respect to x sigma, because r star is a function of g mu alpha and g mu alpha nu. So this term will cancel this one. And here we get that this is equal to 1/2 derivative of m with respect to g mu alpha times g mu alpha sigma. But the derivative of m with respect to g mu alpha can also be written as minus t nu alpha times g mu nu, which we can define as minus t alpha mu in this way. So this can be written as minus 1/2 t alpha mu g mu alpha sigma. And from here we get the equation dt nu sigma with respect to x nu plus 1/2 g alpha mu sigma times t alpha mu equal to 0, like this. And these are four equations which the energy components of matter have to satisfy. Einstein had already found this expression in a previous article from other considerations, but this simply expresses the fact that the covariant divergence of the energy momentum tensor should be equal to 0.